Today we're talking about week 4 homework problems. Week 4 is dynamics, force, and Newton's laws of motion. Now I'm going to start out with problem number 2. Problem number 2 states that if a sprinter from the previous problem, this is problem number 1, which is a 63 kilogram sprinter, starts a race with an acceleration of 4.2 meters per second, what is the next net external force upon him? So this person has an acceleration of 4.2 meters per second and a mass of 63.0 kilograms. And from the previous problem, I'll just tell you that the force that has been exerted is 265 newtons. And so this problem states that the acceleration occurs for a distance of 20 meters. And then he maintains the velocity from that point on to the remainder of the 100-meter dash. So what is the time for the race? So the first part of this problem, the distance is equal to v0t plus 1/2 at squared, and we know that the starting v0 is 0, and so the initial distance is 20, and it's going to equal 1/2 times 4.2 times t squared, and so that t is going to be the square root of 20 times 2 divided by 4.2. So the initial time is going to equal 3.09 seconds. So that's the first 20 meters. The second part, v squared, is equal, so his final velocity after the 20, at the point he gets to top speed, is equal to the initial velocity squared times or plus 2 times a times d, where d here again is 20 meters. So that means that v, his final velocity, is going to equal the square root of 2 times 4.2 times 20. And if you do that, you end up with 13.0 meters per second. 13.0 meters per second, and the distance is 80 meters that he's going this speed, so the time is going to be this 80 meters that remains divided by 13.0, so the remainder of the time is going to be 6.17 seconds. So the total time will be adding these two together, and you get 9.26 seconds for the total race, which is a very fast time for 100 meters, like a world record. So the answer is 9.26 seconds for the entire race. I think the world record is something like 9.8 in that range. Number 4, the next problem, number 4 states that an astronaut in orbit is apparently weightless, but a clever method for measuring their mass is to exert a force and then to measure the acceleration. So if a force of 50 newtons is exerted on this individual, and the astronaut's measured acceleration is 0.893 meters per second squared, what is the person's mass? Okay, so this is the force is equal to mass times acceleration. That's Newton's first law. So the mass is going to equal to the force divided by the acceleration, which is 50.0 divided by 0.893. And so that is going to equal 56.0 kilograms. 56.0 kilograms. Now, the second part of this problem says that exerting this force on the astronaut if a vehicle is what exerts the force, then the vehicle actually experiences an equal and opposite force. So how does this affect things? Well, it does affect things because if you take the measured acceleration, which is this, that's going to equal the acceleration of the astronaut plus the acceleration of the ship. And so the measured doesn't take this into account. Now, the mass of the ship is huge, and so it is negligible. So you end up with the mass of the astronaut times the acceleration of the astronaut divided by the mass of the ship. That's this acceleration right here. Well, you assume that this is much greater than this, and so it can be, you don't have to worry about it, and that's what they do. However, if you could find another source for the force other than the ship itself, say a second astronaut that's not touching the ship, but then you would have to take their acceleration into account as well. And so that's another thing that you could do. The next problem is problem number 7. Problem number 7 states that a rocket sled, this is the rocket sled that actually was introduced in the text, and you have to use that information in order to do this problem, because otherwise you won't know that there are 4 jets, each giving an equal amount of thrust. So this rocket sled has a mass of 2,100 kilograms, and the acceleration, or the force from the rocket sled, the friction force, is equal to 650 newtons. And from example 4.2 on page 133, you know that each rocket has a thrust of 2.50 times 10 to the 4th newtons. And so the question is, if you use only the magnitude of the acceleration, if you use only one rocket. And so, again, F is equal to ma. And so that means that A, now F net is going to equal to the thrust minus the friction force. So it's going to be this minus this. And so F net is going to equal 24,350, subtracting 650 from 25,000. And then F net divided by the mass is going to equal the acceleration. So it's going to be 24,350 divided by the mass, which is 2,100 kilograms, and you end up with 11.595, or to 2 significant figures, 12 meters per second squared. Now, if you take 4 times this, then you get a number that is greater than if you calculate this using all 4 rockets. And why is that? Well, that's because the friction force is a greater proportion of this number. It's a greater proportion of this number than if you take 4 times this number, you're going to subtract the same friction force. And so the acceleration calculated that way is going to be greater than if you just take 4 times this number. And so that's why there's that difference. Now, number 10 states the following. A powerful motorcycle can produce an acceleration of 3.50 meters per second squared when traveling at a velocity of 90 kilometers per hour. So the acceleration is going to be 3.50 meters per second squared at a velocity of 90 kilometers per hour. Actually, let me change that and put that down as 90 so we don't lose track of our significant figures, 90.0 kilometers per hour. At that speed, the forces resisting motion, including friction, air resistance, are total, and I'm just going to put this as FF, they equal a total of 400 newtons. And there is no decimal there, so that's one significant figure. If you have no decimal, if it just says 400 with no decimal, that means that it's one significant figure there. What is the magnitude of force that the motorcycle exerts backwards on the ground to produce its acceleration if the mass of the motorcycle is 200? So the mass here is 245 kilograms. So it asks, what is the force? So the net force is equal to the total force exerted by the motorcycle minus the force of friction. This net force is what accomplishes the acceleration. So that means that MA is equal to the net force, so that the force the motorcycle gives is equal to the MA plus the friction force, which is equal to 245 times 3.50 plus 400, so that the total force is going to equal 1,260 newtons. Now that's the answer they give in the book. Now truthfully, if you were going to do this properly, you would say 1,000, because one significant figure. But I think that's somewhat unreasonable. The more you give, the more you're kind of out on a limb in terms of how precise an answer you can give. You could say 1,300 newtons here and probably be more correct in terms of significant figures than if you said 1,000. But if you say 1,000 because of the fact that this is one significant figure, that would be reasonable. Now another way to look at this is a sum. So this has 3, and this is to the hundredth place. So probably the best answer here is 1,300 newtons, because the sum of 2, you use the hundredths place on this one, and that gives you that. So the best answer here is probably 1,300 to the proper significant figures. Okay, the next problem is number 16. And this will be the last problem on this video. Number 16 states that a brave but inadequate rugby player is pushed backward by an opposing player who is exerting a force of 800 newtons on him. So let's write that down. The force is 800 newtons. The mass of the losing player plus equipment is 90 kilograms. And he is accelerating at 1.20 meters per second squared. So he's accelerating backwards at 1.20. So what is the force of friction between the player's feet and the grass? Okay, so the F net is going to equal the total force that the player is exerting minus the force of friction, and that is going to equal MA. And so F net, so MA is going to be 90.0 times 1.20, and that's going to be 108 newtons. So F net's 108. So F is equal minus 108. FF is equal to, so that's going, and this is going to be pushing him backwards. So this is actually equals 800 minus 108 equals 692 newtons. So the friction force is 692. Now if we call this positive, then the friction force, which is in the opposite direction, would be negative. But if we call that positive, then we would have to call this positive, because this is in the same direction as this. And so this is negative. And so minus 692 is the answer. Again, the hundredths place is the best here, so really the proper answer in terms of significant figures is 700 newtons. Although the book gives the answer of 692. Now the second part of this question is, what force does the winning player exert on the ground to move forward if his mass and equipment's 110 kilograms? So his mass is equal to 110, kilograms. Now his acceleration is the same. It's going to be, let's say this is positive, because everything in the backwards direction, pushing backwards, is going to be positive. And so he's going at the same acceleration as the other player is. And so his force, his F net is going to be 100. And then if you do that, you get 0.42. So 200 times that's 240 newtons. Plus the friction, overcoming friction, 692 newtons. So the total here is 932 newtons. And again, because of, now this, if we bring this down, then it ends up being potentially a confusion in that regard in terms of significant figures as well. Again, the answer given here is 932 newtons in the book. The answer given here is 692 newtons. Now, it asks you to draw a picture for the first situation and the second situation. So if you draw a picture of the first situation, it looks something like this. So for the system A, that is the first problem, you're just taking into account the guy that's moving backwards. And so his backward force is 692, and the total force being exerted on him is 800. So the friction force is 692. Actually, it's going this way against the force being exerted by the football player. The B scenario takes into account both individuals, and this will show you why we had to add the two masses together. Now you have the friction going this way at 692, and basically the MA takes into account this mass, and it's all going backwards at 1.20 meters per second. And so in order to do that, you have to exert a total force of 932 newtons on the whole system. So what the perspective is important in calculating this sort of situation.